me just a second. Okay, so with energy, the work and energy chapter, you're going to have some problems where you just have to find the work due to a force. So that work is given by force times displacement times the cosine of the angle theta. And remember how we talked about how sometimes the work is positive and sometimes it's negative. So for example, if I have an object where the force is in this direction and the displacement is in the same direction, then that's a positive work. And that's because the angle theta is equal to 0 degrees, and the cosine of 0 is equal to 1. So mathematically, that's how that works out. And then, on the other hand, if the displacement and the force are opposite directions, then that means that it has negative work. So if the force and the displacement are opposite, like in the case often with friction, then that's a negative work because the angle is 180 and cosine of 180 is negative 1. Now, this is important because the work-energy theorem says that if I do work on an object, then I change its energy. In particular, we're looking at the change in kinetic energy. So for example, when I do when a frictional force applies work, it usually takes away energy. And that's what this negative here means that the force is taking away energy. And we'll look at some examples from these where these two come into play. So that's one thing, work, and then the work-energy theorem. And then the other thing is when I have systems, like we do the roller coaster problem, when I have an object that has a certain velocity up here, say it's, I don't know, 2 meters per second, and then I ask you what is the velocity at other places along this path. And we'll work some problems in some of the old tests for this. I would give you the initial velocity and the initial height, say the height was 5 meters or whatever, and then let's say I wanted to know what is the speed over here when this object is at a height of 2 meters. Well, I would look at it and ask myself, what types of energy does this object have? So over here, it has both kinetic and potential. And over here, it also has both kinetic and potential. It has kinetic here because it's moving, because the speed is not 0. And it has potential because it's at a certain height. So up top here, it has potential and kinetic. It has potential, which is equal to mg, and then I'm going to go ahead and put in this 5 meters for h. And then right here, it has potential and kinetic. And that's equal to mg times 2 meters, because it's at 2 meters high. And what you would do is you would add up these values and set them equal to these values, and then solve for whatever it is that you're looking for. Now also, say notice, what if I was doing down here, then you would recognize that the potential energy down here at the bottom is equal to 0, because h is equal to 0 there. And so our potential energy is 0. All right, so those are sort of the two classes of problems that you have for Chapter 5. The work-energy problems, just figuring out what is the work done by a force, and then the conservation of energy problems. When I have this object that's changing positions in the gravitational field, changing positions with respect to the Earth, and that changes the amount of potential energy that it has. Let's look at some problems. Let's see. Y'all have, in the workbook, you have fall 15, right? Let's look at fall 16 then. guess I just need to wait. Sorry. You also need to know about conservative and non-conservative forces. Conservative forces do what? They conserve energy, and non-conservative forces do not conserve energy. Non-conservative forces lose energy. You can think of conserve and being sort of the opposite of losing. Like conserve means that it doesn't lose any at all. Raven, how you doing? I'm sorry guys, it's locked up here. Let's see if I can. Okay, so let's look at number 8. This is a nice combination of both conservation of energy and the work energy theorem. So here's a kid that comes down a slide. I'm just going to draw it as an inclined plane. Doesn't really matter in the end, actually. Here's my kid up here, and he says that the slide is 3 meters high, about 9 feet high, and it's 5 meters long. So this distance is 5 meters. And the slide has a frictional force of 10 newtons that acts on the entire length of the slide. How fast is the kid going when he reaches the bottom? So just forgetting about the friction, we can say this guy has potential energy at the top and kinetic energy at the bottom. And I can set those two equal to one another. The potential energy at the top is equal to the kinetic energy at the bottom. All right, the potential energy at the top is m times g times h. And then that's equal to the kinetic energy at the bottom, which is going to be 1/2 mv squared. Now we're not considering the friction at all here. Just sort of forgetting about the friction. But that would be a fine problem too. So here I'd want to know what is the speed. And so the speed is going to be, see, I multiply both sides by 2, divide both sides by m. That gets rid of the m, and then I take the square root of both sides. So it's going to be the square root of 2gh, which is the square root of 2 times 10 times 3, which is 60, which is what, 7 point something? 3. And a 7.7. All right, so that's our speed. That's not the answer here, because I'm looking for now considering the friction. How would you include the friction in this calculation? What is the friction doing to the kid? Doing work on the kid, right? I have a force of 10 newtons that's acting over 5 meters of distance. So how much work is that frictional force doing on this kid in joules? How many joules of work? Sorry, not everybody at once. It's what? What? It's not 5, no. 50, right. So the work done by friction is equal to the frictional force times the distance, which is going to be 10 newtons, times 5 meters, which is going to be 50 joules. That means that he has taken away 50 joules of energy as he goes down this slide. So let's now consider this problem including the friction. I'm going to erase this bottom part here. Oh, I don't like this new eraser. It's like a bad whiteboard. Okay. Now I consider this new problem, the potential energy at the top, and then he loses the work due to friction is going to equal to the kinetic energy at the bottom. He had this much energy at the top. He loses some of it due to friction. Work is equal to force times distance. That's 50 joules. And then that's going to equal the kinetic energy at the bottom. And so now I can put in some numbers here. The mass, which is 10 kilograms, g, which is 10 meters per second squared, times the height, which is 3 meters, minus 50 joules. That's what we found up here. is going to equal to 1/2 of the mass, which is 10 times v squared. Turns out I have to keep the 10 because it's not in the work calculation. And then I solve that for v. So that's 300, 250, 50. Well, it turns out to be 7. Right, is that right? Does anybody know? Yeah, the answer is 7. Okay, so those are two good problems. Those would be sort of two separate problems, one without friction and one with friction. But the more difficult part is including that friction and understanding that the friction actually takes away energy from that system. Okay? Friction is what type of force? A conservative or a non-conservative force? It's non-conservative force because it loses energy, and that's what it's done in this case. Okay, let's look at some others here. Okay, number 6 is good. We haven't talked about this today, but it's very similar to the ones dealing with gravitational potential energy, except instead of dealing with gravitational potential energy, you're dealing with elastic potential energy. So what you have here is that you have a 2 kilogram steel ball, and it falls onto a spring like this that is a spring constant of 250 Newton meters. And I want to know if the spring compresses by 1.1 meters, then what height was it released? So again, think about the energy. What type of energy does this system have? Initially, the ball has what type of energy? Elastic potential, gravitational potential, or kinetic? That's right, gravitational potential. So it initially has gravitational potential energy. I'll call that PEG. But then down at the bottom, it falls and it gains kinetic energy. But once it hits the spring, it compresses the spring and stops. What type of energy does it have now? That's right. It has potential energy of the spring. So down at the bottom, it has, which I'll call PES, elastic potential energy for the spring. We just set those two equal to one another. PEG is equal to PES. Goodness bless you. And that's equal to mgh equals 1/2 kx squared. Again, all these equations are on your equation sheet, which you'll have on the test. I'll print it for you and give it to you. But you need to be familiar with what's on there. And then here you would solve for h. H is 1/2 of k, which is 250, x, which is 1.1 squared, divided by mg, which is 2 kilograms and 10. Oh, I get 0.03. That's not right. Oh, I get 7.6. Anybody else get that? Y'all agree? Yeah, that's equal to 7.6 meters. That's a good conservation of energy problem. Okay. Any of these others look like something y'all want to talk about? Any particular problems regarding the conservation of energy? I'll think for just a sec. I'll sort of stroll down through here. But if there's one that you want to look at another test, then I can do that too. There's one like the roller coaster problem. You'll probably see one of those. Number 5 is similar. How would we go about this? It's similar to the other one with the spring. But in this case, what type of energy am I converting from and to? What kind of energy does it have initially, this object? It has potential. What type of potential? Gravitational or elastic potential energy? Elastic, right. It's like those spring-loaded guns that you had up in the lab. You pull that spring back and compress it, and then you release it, and it hits the little ball and gives it kinetic energy. So here you would say the elastic potential energy, 1/2 kx squared, is equal to the kinetic energy, 1/2 mv squared, and then you'd be solving for v. So see these conservation of energy problems, they are all basically the same. I'm just going from one type of energy to another. And you have to be able to identify from reading the problem what types of energy I'm dealing with. Sometimes it's going to be kinetic, sometimes it's going to be elastic potential, sometimes it'll be gravitational potential. Okay? Sometimes, like with number 2 here, you'll have both. I have both kinetic and potential. Wait, why do I have both here? Because it's moving, right? Because it's at some height and it's moving. And then I also have the same here, both elastic and potential. And so you'd say this energy is equal to this energy. Okay? What about, oh, here, actually, for this one, at point E, what type of energy does it have here? It comes up and it stops. It has gravitational potential energy. So all these problems are largely the same. Let's look at number 1. It takes 100 meters to stop a car initially moving at 25 meters per second. Under the same conditions, how far would it take a car traveling 50 meters per second to stop? It might look really unfamiliar to you, but we actually had a problem similar to this in the concept test. Remember with the truck moving up the hill and stuff like that? So it's a little bit different, though. It sort of brings several ideas together, so let's look at it. If I increase my speed by a factor of 2, by how much have I increased its energy? I've increased it by 4, because my kinetic energy is 1/2 mv squared. If I double my speed, I quadruple my kinetic energy. So when I go from 25 to 50 meters per second, I quadruple my energy. I've doubled my speed, but I've quadrupled my energy. And when it had, the original kinetic energy, it took a distance of 100 meters. That means that some force had to work on that car over 100 meters in order to make it stop. However, when I have 4 times the kinetic energy, the question is, what distance is required now? Well, the work is being done on that object still, but now I need 4 times the work because I have 4 times the energy. So what is the distance going to be? Under the same conditions, by the way, that means that you have the same frictional forces on the road, whatever the car is, the way you stop. So what is the force, what is the distance now required? 400 meters. 4 times 100 meters, which is 400 meters. Notice there's some other stuff there about conservative and non-conservative forces, and you need to know what those are. You need to know conservative forces conserve energy. Field forces are a type of conservative force. Let's see, this is not true. What is it? 2 and 2 is the only one that's true. A is the only one that's true. Because conservative forces conserve energy. Non-conservative forces do not conserve energy. Conservative forces are path, dependent or independent? Do they depend upon the path, conservative forces? They do not. They're independent. Right? Because I can go up the mountain this way, or I can go up this way, and my potential energy still changes by the same amount. It's independent of path, the work done by conservative forces. And then some examples of conservative forces. Conservative forces are all field forces, because anytime you have contact between 2 surfaces, I begin to lose energy, because frictional forces take place. Okay? All right, y'all want to look at momentum now? Is that okay, or more energy? We'll address energy again next week. I'll have another help session the day before the exam on Thursday at some time. Do y'all have a particular time? If I had it at 2, would that be okay? Or do you prefer 3? 2? 3. All right, I'll just look at my schedule. I'll decide. I'm sorry. I wish I could do it both, but okay. So with momentum, you need to know a few things. Really, just sort of how to calculate momentum. P is equal to m times v. Know that it's a vector quantity, so it does have a direction. And then we had 2 big ideas that came up in this chapter. F is delta P over delta T. Remember, this is just a rewriting of Newton's second law. because delta p is m times delta p, and delta v over delta t is acceleration. So this is just Newton's second law, nothing fancy about that. And then also, we said that the initial momentum is equal to the final momentum. That's conservation of momentum. And then we had some details in that with elastic versus inelastic. And you need to know, kind of like with the conservative forces, what those various things are. And then we also had perfectly inelastic. That's where they stick together and move off in the same direction. No 2D problems. You did have a 2D problem on the OpenStacks, just that one where you had the block moving down and one moving to the side, and then they stuck together and moved off in the same direction, but you won't see any of those. All right, that's it for that chapter, but let's work through some examples. We'll go back to that fall 16 exam. This is a good example of a collision problem. You'll probably have one very similar to this. We have two objects that are moving in a certain direction with a certain speed. Either they stick together or they bounce off one another, and you have to figure out what is the speed of one of the objects. There we go. So the hard part on this is figuring out the initial and the final, although in this case it's pretty clear what's initial and what's final. And then figure out which things are involved in the system. So in this case, I have two things involved in the system, ball number 1 and ball number 2. So this is my initial, PI. This is my final, PF. And in all collisions, whether they're elastic or inelastic, every collision in the universe, this is always going to be equal. For a system of particles, the total momentum will always be equal, assuming there are no outside forces on them. So I start with the first one. I have mass times velocity, that's 2 times plus 4, positive 4 because it's to the right, plus 4 kilograms times V2. I don't know the direction of that, although you can probably guess what the direction is. Is it going to be positive or negative, you think? Left or right? It's going to be to the left. And I know that because if this guy is going to the right, and these guys are going to the left, this one has to be going to the left because it has momentum in that direction. And the final situation, the two particles have a negative momentum. So I could go and get rid of these options. I know they're not right. They are right, actually. That's why they're wrong, because they're to the right. You get it? Friday afternoon, huh? Like, there's no humor on Friday afternoon. Is that the thing? Did y'all really want to come here on a Friday afternoon? It's okay, you can be honest. You did? Not me either. Okay, so 2 plus 4. No, I like coming. Why 2 plus 4? They stuck together. Right, so times 5 meters per second. Oh, but I made a mistake. Look at me. I just missed the problem. It's negative 5 because it's to the left. Okay? Be very, very careful with your signs, especially in this chapter. The signs are pretty important for this chapter 6. 8 plus 4v2 equals negative 30. What's that? Negative 38 divided by 4 is going to be 9.5. Is that right? Yeah, 9.5. Negative 9.5. The other class of problems that you'll have are these impulse problems, like number 14. And you had some on your OpenStacks. Listen, I picked a bunch of questions on your OpenStacks that I think would make excellent test questions. They're about the right difficulty, so... Am I winking? Is this a wink? Not really. I'm not very good, but do you understand what I'm telling you? And I'm going to pull a number of questions from that OpenStacks. I'll change the numbers, of course, so don't just memorize the numbers, but they should look very familiar to you. And, you know, they're a lot like some of these questions, too. All right, so number 14 here, this is where I'm looking at my impulse, F equals delta P over delta T. When I say impulse, remember that's just another word for change in momentum. All right, it's also a word for force times time, which is a change in momentum. I know that this is that type of problem because there's only really one object in the system. That only one object is moving. It's not colliding with another object and making it to move. Now you might say, well, the ground's involved in this collision, but the ground ain't moving. Okay, that the ground is stationary. So that's how I know that I'm using this equation, and then also because it's asking for the force. That usually there will be some force involved in this class of problems. So F is equal to delta P, that's mvf minus mvi over delta T. The mass is 0.2 kilograms. I'm going to go ahead and pull it out because it's common. Again, the signs are really important here. Sometimes I find it useful to draw a picture. It's minus 3.6, and then it's going up at positive 6.4. This is VI, this is VF. You know, take 30 seconds to draw a picture, especially if you're not really sure what to do. It'll help you to think about what's going on in the problem. So to find my final minus initial, it's going to be 6.4 minus a negative 3.6. And that's all over delta T, which is 0.03. And so that's 2 divided by 0.03, I think. 67. So D is the right answer there. Okay? So those are two classes of problems. You'll have several of each, probably, for the collisions and for the impulse momentum problems. I say several of each. You'll have a couple of each, probably. Number 13 is another collision. You'd work it very similar way to number 12. And then we get into rotation. Any particular problems on this chapter? How y'all feel about chapters 5 and 6? I think they're all right, actually. But you might be struggling with them, and that's okay. But I think you need to master both of them. You need to master both chapters. All righty. You want to look at chapter 7 while we're here? While we're here, okay? For all the effort to come out, let's look at chapter 7. So chapter 7, I'm going to send a note out. If you haven't gotten that, if you're not in the class, you'll get a message later. But chapter 8 is not going to be on the exam. It'll just be chapters 5, 6, and 7. No chapter 8 at all. Though in the in-class section, we're moving on with chapter 8, and so I'm going to recommend to the online students that y'all also move on with chapter 8, just so that after the exam, you're not like all of a sudden, we're almost through with chapter 8, because we're moving pretty quickly through chapter 8. So I recommend that you just sort of continue on with chapter 8, but I'll send my online students a message about that later, okay? But I just want this to be not an easy exam, but I don't want it to have too much material on it. But I think it will be easier than previous exams. Okay, so just sort of have some details about rotational motion that you need to know. Like you'll certainly have some conversions. Useful to know your unit circle, 0 radians, pi over 2, pi, radians, that's a pi. 3 pi over 2, and 2 pi. When we go around a unit circle, we go counterclockwise. Those are our quadrants. And we go in this direction, starting with the positive x-axis. So counterclockwise, we call positive. Clockwise, we call negative. You need to know your conversion factors. Radians is the SI unit for displacement. And you can never go wrong with radians but I will give you some measurements in revolutions or in degrees, and so you'll need to know how to convert. And so you need to know that 2 pi radians, that's a circle, is equal to 1 revolution, is equal to 360 degrees. I think you know that, all of you, or at least in the recesses of your mind, you've heard it before. You need to know for your kinematics, I recommend that you sort of cement these in your mind, that before when we talked about linear displacement, now we're talking about angular displacement. Before where we talked about linear velocity, now we're talking about angular velocity, or omega. And before we were talking about acceleration, now we're talking about angular acceleration, or alpha. And these are all in radians per second, or radians per second squared. But you can express them in revolutions or degrees. Revolutions per second squared. All the same equations that we used before are still going to hold. That is that theta is equal to omega naught t plus 1/2 alpha t squared. And look, if you forget what is omega, what is alpha, and all that, then you can look on your equation sheet where you'll find this, and then that will, I think, sort of jog your memory as like, oh, v used to be here, so this is my velocity. Or a used to be here in the t squared spot, and so this is my acceleration. And then we also had our velocity equation, omega equals omega naught plus alpha t. We'll look at some kinematics problems before y'all leave. We'll do some examples, but you'll have some. They're going to be largely sort of plugging in, knowing how to use these equations, and knowing what these various values mean. You also need to know centripetal forces. So when we're talking about centripetal motion, that means that an object is moving in a circular path around a fixed point. It has a certain acceleration. Because the velocity is constantly changing direction, it has to have an acceleration. And that acceleration is our centripetal acceleration. It's equal to v squared over r. And then because we have an acceleration, I also have a force. So that F, that centripetal force, is going to equal to mv squared over r. This is on your equation sheet. I don't think this is on your equation sheet. I'm pretty sure it's not. But it comes about from Newton's second law. That if I want to know the centripetal force, that's just the mass times the acceleration. And this acceleration is v squared over r. Remember, it's your responsibility to know what's on that equation sheet. Not to know it, but to be familiar with it. And so just have it out as you're going through your homework, practicing the old test. Have that out next to you, sort of recreate what it's going to be like on the test. Let me go back to that previous slide, because I forgot to say something. We can translate our angular to our linear quantities in this way. X is equal to theta times r. We just multiply them times the radius. V is equal to omega times r, and A is equal to alpha times r. And that allows me to convert them to my linear quantities. So if I have, for example, a circle of radius r, and I move through an angle theta, this is the distance, theta times r. All of these, by the way, when you're doing this, have to be in radians. Right, so those are just sort of a lot of details that come up. There's really a lot of details in this chapter, really building up to chapter 8. We should just have chapter 8 on this test. Yeah, it would be really good. But I've already told you, right? Did I already tell you that? No, chapter 8. That was good. All right. The centripetal force is a force that's provided by something. So like, for example, here, my centripetal force is my tension in the string. And if I want to know the tension in the string, for example, and if I know the speed, then I would just do the speed squared over the radius times the mass. Let's just look at some sample problems, okay? I think that's best treated there. Let's look at 21. This is a good just kinematics problem. I have a tire. I want to know how many radians does it rotate after so many seconds, after 5 seconds, with a acceleration of 2 radians per second squared. So I'd say theta is equal to omega naught t plus 1/2 alpha t squared. I'm sorry, first what I would do is I'd just write down everything that I know. I know that alpha is equal to 2, t is equal to 5. I know that omega naught is equal to 0, and I want to know what is theta. Well, I also know that r is equal to 0.3, but it turns out I don't need to know r. It's not important for this problem. Because I'm looking for theta, I know that at least eventually I'm going to have to use this equation, because it's all that I know to give me the angular position. Omega naught is 0, so that goes away. And so this just becomes 1/2 alpha, which is 2 radians per second squared, times 5 squared, which is going to be 25 radians. I didn't write down my units here, but just be aware of your units, because sometimes on these I'll give mixed units. I might give this in revolutions per second squared. Now, you don't necessarily have to convert it to radians, but if you don't convert it to radians, it ain't going to give you radians in the answer. So you never go wrong converting to radians, because that is the SI unit, but it's not always necessary. If you're uncertain, just go ahead and do that. Let's see, pi radians. How many revolutions is pi radians? What is it? It's a half, right? So pi radian is a half a revolution. You can do your conversions, and you'll probably have some conversion problems like this, where if I have pi radians, just like we did in chapter 1, use your conversion factor. 1 revolution is 2 pi radians, and so the pi's cancel, and it's going to be a half. Oh, I like this one. The second hand of an analog clock has what angular speed? Between 0 and 30 seconds. Well, if you think of a clock between 0 and 30 seconds, it moves through, what was that, 90 degrees, which is pi radians. So it's pi divided by 30. That's 3 over 30, which is 0.1. Okay? So expect some sort of basic idea problems about rotation like those, converting or sort of thinking about rotation in that way. Any of these stand up to you? How about number 20? Let's look at 20. It deals with centripetal forces. So this is the gravitron. You know, like one of those things where you stand up against the wall and it spins you around and squishes up against the wall. I want to know what is the value of the centripetal force. Now the first problem asks you what's providing the centripetal force. What is actually forcing you into that circular path? And it's the wall that's pushing back against you. That's actually pushing you into this circular path. If you have something that's on a rope like this, then the centripetal force is provided by what? The rope, right. The tension in the string is the centripetal force. Or if you have a car that's going around a curve, it's the static frictional force, the frictional force between the tires and the road that is providing the centripetal force. But in this case, it's the normal force, the wall you stand against that pushes on you. Now I want to know what is the value of the centripetal force. So this centripetal force is equal to m times v squared over r. I know that's the case. And so now I want to look in the problem and see, what do I have? Well, there's my mass, 70 kilograms, and there's my radius, and it tells me that it spins at 2 revolutions per second. So should it just be 70 times 2 squared divided by 5? No, you got to be careful here. Make sure everything goes into radians. In fact, this is not even v. This is omega. And so I need to convert that to v. So first, omega is 2 revolutions per second. Let's go ahead and convert that into radians. 1 revolution, 2 pi radians. So I'm going to say that's 4 pi radians per second. So that is my angular velocity. And then V is equal to omega times R. That's going to be 4 pi times 5, which is 20 pi. So now I'm ready to put in my answers here. So I have 70 kilograms, that's the mass, times 20 pi squared divided by 5. So that is 70 times about 3,600, because 20 times 3 is 60, and then squared divided by 5. What does that give me, y'all? 5, that's 14 times. Is it E? E the right answer? So E is the right answer. Okay? You pre-med folks, you need to learn how to not use your calculators. Because you need to be able to deal with numbers like that, even more complicated numbers without a calculator. Every year I say, I'm not going to allow them to use calculators on their tests. But then I always wimp out at the end. Because I know that some of you just, I don't know, it makes you feel more comfortable to use it, right? Make you feel better. Okay, let's see what else we got. Oh, we're not doing any torques. So as you're preparing for your exam, if you see any business with torques, then you won't see that at all. So no chapter 8 on the exam. So on this exam, we stop at 24. Okay? But any other questions here? Thing that's nagging? I know y'all probably haven't started. I mean, some of you have been studying, but you haven't started studying yet. Have you? 20 minutes a day? Some of you maybe? That's the way you do well. 20 minutes a day. I'm learning to play the piano. Did I tell you this? Do you think that I can sit down just before going to see Miss Margaret and learn all the pieces that she gives me? No way. And she's hard, man. Like, she'll slap you on the knuckles. Okay. Well, we'll stop there. I know it's a little short, but we'll stop there nonetheless.